Okay, so it's a pleasure to have Shaun Hampton to talk about bootstrapping, the effect of the twist operator in 2D conformity theories.
Okay, can you hear me? I think so. Okay, thank you all for being here. Just want to thank the Lord for being here. I thank Nick and Joseph and Andrea for putting together this great conference, and thank you all for being here to listen. And I also want to thank Ben, who's my collaborator, who has been really great working with him. So today, we're going to switch it up a little bit now. We're going to talk a little bit about CFT. And particularly, I'm going to be talking about something called a twist operator. This is very relevant when you're looking at considering like microstates, and you're considering a lot of the twist. We have something called twisted sector states, and I think in the two-charge case, this is especially relevant in the D1, D5 system, where you have various twist sectors, and they can be related to, or they correspond to microstates in the dual gravity theory. So that's what I'm going to be talking about today. And here's just an outline. So and this goes under the name of an orbifold CFT. So I'll review that, the orbifold CFT. Then I'll talk about the effects of the twist operator, like what type of processes arise as a result of this. And then I'm going to talk a little bit about sort of the traditional ways and methods in which quantities have been computed using the twist operator. The main way being the covering space method. So dealing with this idea of covering maps. I'm only going to spend just a slide on this because I want to get to what we did recently. Then I'm going to talk about something called a Bogle transformation, which most of us are probably familiar with. You see this in quantum fields and curved space-time. But this type of transformation is very relevant when you're considering a twist operator. So then I'm going to talk about some of the work that we've done recently, me and Ben, on bootstrapping the effect of the twist operator, which is a way without using this covering map, but using conformal symmetry and some of the generators of the Virasoro algebra. And I know there's also been work done on that by Andrea and Dade and Lorenz Eberhardt. They were computing twist correlators in that way. And so at the end, I'll just conclude and talk about future directions. So I'm going to be, what I'm talking about is relevant for the D1, D5 CFT, but we're going to consider just a simple scenario here with just one free boson. So what is an orbifold CFT? So let's consider we have n copies of a boson X in the complex plane, and let's consider some target space to, let's say, the real line. So an orbifold is going to be, we're going to act on n copies of the target space with some group. And the group that we're going to use is called the symmetric group. And so let's see what comes out as a result. So I can have something called a singly wound sector. And this is where, as you go around 2 pi in the complex plane, the fields just go into themselves. So there's nothing special that happens here. And this is considered the singly wound sector. But I could have something called the k wound sector. So let's take k copies out of the n total copies, and let's act with something called a twist operator of order k. And so as we go around 2 pi in the complex plane, so what's going to happen is x1 is going to go into x2, x2 will go into x3, and so on and so forth up to xk, and then xk will go into back to x1. And the remaining copies will just go into themselves. And so this is the action of a twist operator, and this is what you would consider an orbifold. And we're using this permutation group. We're permuting the copies into each other. And the conformal dimension is given here. This is just a one free boson, so C is 1. And the conformal dimension of this operator is given here. So you can also use, we're in the complex plane, so you can use radial quantization if you want to define oscillator modes in this theory. And so in the untwisted sector, the way I define a bosonic mode, an oscillator, is just I have the bosonic field x, so partial of x really. I weight it by z to the n, and I do a contour integral. And this is this defines for me a bosonic mode in the complex plane. And I can compute the commutation relations using OPE expansions of with del x, and you can get the commutation relations. So in the untwisted sector, here n is an integer, but in the twisted sector, n is actually is fractional, and you can it's here. Can you see the pointer? Not okay. It's n equals q over k, where k is the winding and q itself is an integer, and likewise you can get the commutation relations. So what is the effect of the twist operator? What types of things happen when we apply the twist operator to, say, a collection of bosonic modes? So here, in the rest of the talk, I'm going to, well, except for the n, most of the talk I'm going to restrict myself to n equal to 2. And so consider an arbitrary number of bosonic modes in the initial state. And I can apply a twist 2 operator at z naught in the complex plane. And so a natural question would be, what is the final state, or what is the resulting state of this action of we call sigma 2 acting on these bosonic modes? And what types of effects can we get? And so here, this picture here is just a schematic of what's going on. And actually in the picture, I only have 2 modes. So you see these 2 circles here. Those represent 2 bosonic modes in the initial state, and we place the sigma 2 at z naught, and it basically creates a branch cut from there to infinity. So anywhere after z naught, as you go around, it's a double sheeted covering, and so what type of effects do you get from a twist operator? Well, there's 3 main effects that you get. And anything else would be a combination of these 3. One process that we get is something called a contraction. So consider 2 modes in the initial state. If there was no twist operator, they would commute with each other, and there would be nothing interesting. But when you apply the twist operator, because you're changing the boundary conditions of the fields, there is an opportunity for them to talk to one another. Then you have the propagation. And propagation is you have a single mode in the initial state, and what the twist is going to do is it's going to produce an expansion of bosonic modes in the final state, but they're going to be weighted by this function f of I, which basically tells you the probability that that mode will be populated in the final state. And so a third type of effect that you get is when you act on the vacuum, you actually produce pairs of bosonic modes on a doubly wound copy in this in this exponential of bilinears. And actually, we can understand this in quantum fields and curved spacetime. You see this effect where at some initial time you may have a vacuum defined, and at some later time the vacuum is changed, and so the oscillators defined in terms of the first vacuum are not the same as the oscillators defined as the state has evolved. And so, and I'll talk a little bit more about that when we get to the Boglebuff transformation. So here's more specifically what we would consider. So, like I said, you consider a single mode in the initial state. It acts on a single bosonic mode, and what you're going to get in the final state is this linear combination of bosonic modes weighted by Fi, and then you're going to and then you're also going to have this exponential of bilinears here in the final state. And if you consider 2 modes, what you can get is sigma can, the twist operator can act on each of the bosonic modes where they don't hit one another, but the sigma just hits each one, and so you're going to get basically two linear combinations multiplying one another. But then there's another term where they could hit one another, and so then you get this Cij, and so I and J here are the copy indices. You could have 1 1, 1 2, 2 1, 2 2, and so these two, and of course the one where it acts on the vacuum. These are sort of the main effects that you can get, and if you added more oscillators, they in some way the effect is going to be related to these three. And so here is just another schematic now, a little bit more detailed of the process. So we have two contours in the initial state, and we see the contraction is sort of represented by a line that goes out and comes back to itself. It just represents that the two modes are contracting. Then you have a propagation, which basically the two modes are passed through the twist, where the twist hits them and creates this linear combination. And then you have the pair creation in the final state, and of course you see this branch cut because of the presence of the twist operator. And so these quantities, which we name gamma, F, and C, a lot of these have been computed, or these have been computed for using this twist operator by these authors here, and of course David is in the crowd. We've done a lot of work together on this. And as I said, this operator creates a branch cut between Z naught and infinity. So in the Z plane, if you have this bosonic field, and so as you go from 0 to 2 pi, you can say X is equal to the segment X1. As you go from 2 pi to 4 pi, you can say X is equal to X2. But 0 to 2 pi is kind of like the same as 2 pi to 4 pi. So really, the problem is that X is actually double valued. It's sort of equal to X1 and X2. And so what you have to do to resolve this issue is you have to map to a covering space where you sort of resolve this double valued issue, this double valueness. And so here I just present, yes?
That's a very nice question. Since S2 is also Z2 in a sense, because you can, why don't you work with X1 plus X2 and X1 minus X2? X1 plus X2 would not be touched at all by, and so this is only an abelian orbifold of X1 minus X2.
You're right. You're right. Yes. So actually, I think I don't show that in the presentation, but you're basically talking about a symmetric combination of X1 and X2.
Yeah.
Which it doesn't see the twist.
X1, yeah, it's
that's right.
Touched. Only X1 minus X2 is touched on.
That's right. That's right. So yes, if you consider that particular combination, it's untouched. But if you want to see some non-trivial effects, you can look at maybe the anti-symmetric combination or
sure. But then it's only the abelian orbifold. It's a standard Z2 orbifold.
There's one question. Is it like for general N that you can do this, or it's just like because it's
no, for general N, clearly the situation is more complicated because at N it's not a group. But
exactly.
For Z2, I don't know.
But he's setting up the formalism for general N, but it's easier to describe pressures to it.
Okay.
Yeah. And as I say here, as the number of twist operators increase, the covering map becomes much harder and harder to find. Actually, it becomes harder quickly, and so we like to, if there's another way, we like to try to figure out how to compute some of these effects. So I just want to sort of mention this Vogel-Buff transformation, which basically, if you have, so say I have a set of operators A and A dagger, I can write those as a linear combination of some new operators B and B dagger. And so I have the vacuum with respect to A hat, and I have the vacuum with respect to B hat. But the A vacuum is not the B vacuum. And so if we just we follow these equations here, we find that the A vacuum can be written as sort of this exponential of bilinear excitations on the B vacuum. And so as I was saying earlier, in quantum field and curved space, you see this phenomenon happen because basically, for example, if the space is expanding in time, the time coordinates actually changing, so the way energies are defined is different at different times. So I'll wait till the time to go home. And so we can see here. So if we act with A dagger, given these definitions here, we see this relation here. And actually, what you begin to see is sort of the similarities between this state and the effect of the twist operator. And so, as I was saying, if you wanted to actually sort of make a maybe make a correspondence, write it in a way like we wrote it earlier. So this C now is B star, beta star, alpha star. And we see that the propagation is given here, alpha star plus beta star gamma. And then, of course, you have this pair creation. But in this case, the coefficients are not completely independent of one another. It turns out that this gamma here is actually equal to minus beta alpha. And so, in the work we basically said that we'll call this a normal Bogleubov ansatz, and this is work that David and Samir and Zach has done previously, where they looked at this Bogleubov transformation as it pertains to the twist. So I think they looked at they looked at a sigma 2 or two single wound copies being joined together, but I think they also looked at the M and N case. So if you want to look at make the correspondence, this is just a schematic. Operators are now promoted to infinite dimensional vector, a vector of operators, because now you have a tower of modes basically. And so these coefficients alpha, beta, and gamma are promoted to infinite dimensional matrices. And so here's just, for example, alpha goes to alpha ij. So this involves actually inverting an infinite dimensional matrix here. So think of this now as a matrix multiplication. But what we're going to do in this case, we're going to discuss, say, for example, what we call a weak Bogleubov ansatz. So we're not going to impose this relation on gamma, but what we're going to do is try to use conformal symmetry, the Virasoro generators, to help us to compute these quantities. And the goal is to not have to go to the covering space. And so, as I was saying, David and Samir and Zach, they've made progress in other ways of computing these things before. And so, here, this is the weak Bogleubov. So we're going to take this ansatz here, which is natural because we already know the answer. The thing is, we know the answer, but the goal is to try to use this to go to maybe do more complicated situations. And so what we're going to do, some of the main calculations will be done with, say, the conformal generators of the conformal algebra. These are the global generators, L1, L-1, L0, L1. And what we're going to do is obtain recursion relations, and this is all in the Z-plane. And so just want to highlight the previous work, which is I've already mentioned that David and others have worked on this using this Bogleubov ansatz. There's also was some other work where there was a combined use of the conformal symmetry, but also the covering map to analyze the pair creation. And then, as I stated previously, Andrea, who's going to be talking later in the conference, and his collaborator, they use conformal symmetry to compute twist correlation functions. And so what we're looking at is effects of twist operators, like the propagation, the contraction, and so forth. So now let's discuss some of the work that we've done recently. We'll call it bootstrapping the effect of the twist operator. So what's going to be important is using the Virasoro generators. This is a 2D conformal field theory. So we're going to use the Virasoro generators. And so here I've just defined the generators in the untwisted sector and the twisted sector and their respective commutation relations. So what we're going to do is we're going to use these generators to produce pair creation, to try to reproduce propagation, and to try to reproduce the width contraction term. So first, let's look at pair creation. How do we sort of bootstrap this quantity? We're going to use L minus 1, and L minus 1 acting on the vacuum is 0, and so we use this conveniently. So then we can apply sigma to L minus 1, and imagine now taking the L minus 1, and we know it's 0, so let's move the L minus 1 through the sigma into the other side, so you get two terms. You get a term where the L minus 1 hits the sigma, and then you get a term where the L minus 1 is acting on the left of sigma. And so the commutator, as you can work it out, is it actually ends up being just a partial derivative acting on sigma 2. And so then we can write this relation that's equal to 0 as this here. And we know what sigma acting on the vacuum is. We know that that's just going to give us this exponential of this sum over bilinears that's weighted by these gamma coefficients. And so one can match terms here. And so you're going to get some type of consistency conditions. And this is in general kind of what the equation looks like that you're going to get. You're going to get, on one side you have sort of the partial of some gamma, and on the other side you may have some shifted indices. And so once you choose, for example, the way that you can sort of resolve this recursively is once you know gamma 1 half, you can use this equation and you can solve for gamma 1 half, 3 halves, so you can go the other way, and so you can sort of fill out this space, and you can find a nice recursion relation that gives you the full expression. And so if you solve this, you get this expression here, and this actually matches the form of the expression that's given from the covering space method. And so
how did you get gamma half?
That's okay. So actually, the only modes that are affected by the twist, the only non-trivial physics comes when the modes are half integer after the twist. The integer modes sort of just pass through the twist, and there's no effect. So that's why you get this half integer modes. Sorry. Okay. So we can use yes.
I don't think. So you give us the recursion relation for everything, but how do you get the bottom one? Or is that?
You get the bottom one. You have to apply a boundary condition in the initial state, I think. So I think you can take. So you have this z naught here. I think you can take z naught. So if you take z naught to 0, there's some condition that the gamma. I think the gamma should be 0 there. And so if you plug in that condition, that's how you get gamma half. So then from there you can get gamma half out. Yeah. Sorry. So there was a boundary condition there. We just sort of carry this process through with the other quantities. So if I want to compute L minus, the effect of the propagation, I know that alpha 0 acting on the vacuum is 0 because the center of momentum is not moving, and so then I can apply sigma on this, but then I can rewrite alpha 0 using the conformal algebra as L1 acting on alpha minus 1, and then I do the same thing. I move the L1 through to the other side, and I obtain sort of this equation here. And if I apply this sort of this operator, I guess you could call it an operator here. It's an operator. I can apply this on this state here, and when you do that, and when the dust settles, there's some calculation that's involved. But when the dust settles, you obtain again another sort of consistency equation, and which you can solve recursively. And actually, so in this case, if you see here, this sigma 2 acting on alpha minus 1, we know what that is, and or we know the transformation that produces. So there's the initial mode is a unit, 1 unit, and so so here this the f function that we find is -1 unit in the initial state and an arbitrary moding in the final state. And again, these p is this is post twist, so this is on the W1 copy. So the modes are half integer. But then we need to do a little bit more to get the full expression. And so what we do is we can use we can again use these L-1s recursively. There's a convenient way to write the equation such that you can compute this generally. So if you know f of -1 minus p, then you can use L-1s to get you f of -n minus p. And this constant c here actually, so this is, we had to use a relation with L-2, which is not the global algebra, but nonetheless, it's still one of the Virasor generators. And so we were able to actually compute this c, we had to look at a contraction term, which is what I'll talk about next. But here, just want to, so you get sort of two scenarios here. So one, so you can have, so these f functions can be defined starting with an initial mode on copy 1 or an initial mode on copy 2. And it turns out that if p equals n, you get a factor of a half. But then that's the only integer moding actually you can have, is if the mode stays itself. But in the half integer case, you get this expression here. And then if I want to compute f2, if you think about what the copy 2 is, it's just sort of a 2 pi shift of copy 1. And so if I shift z naught, if I shift the angle by 2 pi, because the power of z naught is there's half integer, I'm going to get a minus sign because I've shifted it. Essentially, you get an e to the minus I pi, or e to the I pi factor. So now I want to compute the width contraction terms. And so now I have two modes in the initial state because I want to consider a case where they contract together. And so I can, again, using the Virasor algebra, I can rewrite two alphas in the initial state conveniently as an L-1 acting on maybe two alphas shifted where one of them has been shifted. And I again obtain an equation which will give me it'll give me a differential equation to solve. And so we know what so we use the ansatz for the two modes, and we insert this ansatz sigma 2 alpha alpha. We insert it here with the appropriate mode numbers. And again, we obtain another equation, consistency equation. And so we can solve this. So basically the idea is similar each time. It's just a different function. And so we solve this recursively, and we can find C1n for the copy copy ij. And again, using L-1, we can find the further recursion relations, and we can solve. We can find a general contraction term. And so these are the three main quantities that one would like to compute as effects of the twist operator. And so what we've done is we used what we call the weak Bogomolov ansatz. We didn't impose the condition on the gamma. The gamma coefficient, and so instead we replace it with using the conformal symmetry, the Virasor generators. And so we computed pair production, propagation, and width contraction. So the good thing is this requires no knowledge of the covering map. So the hope for doing, so this was nice to reproduce, to show that we could reproduce what's already known. But the hope is to be able to compute effects of higher order twists, because I have in mind, of course, so this is just simply a one boson, but if you look at the D1, D5 CFT, it's morally the same. It's just you increase the number of bosons, and it's also super symmetric. And so there, if we can somehow compute effects of higher order twists, maybe it's maybe a little too ambitious, but maybe maybe we compute some things non-perturbatively in the CFT in this orbifold CFT, which if using the covering map, it's once you get to maybe 4 twist operators, it becomes unwieldy and unfeasible to try. I mean, you can try it, but it becomes really tough. I guess you have to maybe take some limits or things like that. So we looked at a case for a multiple twist, a higher order twist. So I'll try to see if I can explain it because I'm still trying to sort of absorb it myself. This is not in the recent work that we did, but this is something we hope to sharpen in the future. But consider I have K twist operators, and let's take an odd number of them. So I start off with 2 single one strings. I can join them, I can split them, I can join them, I can split them. So let's end up. So we want to end up in a doubly wound state, and we want to consider K to be large. And so so you can we know that L-1 acting on a vacuum is 0, so then we can pass the L-1 through, and we obtain a sum of partials. But if we consider, what we want to consider is a disk that these K operators, a large number of K operators are randomly distributed in a disk that's centered around 0. And so, because there's so many of them, it seems like that the higher order modes that there's not going to be really any effect from higher order modes because you basically have sort of short wavelength processes because the twists are so close together. And so what essentially you can treat this sum of partials, these sum of partial operators. You can almost treat it like K times a partial operator where the variable is the central guy. It's at the center of the disk, and so it's almost like you move the whole disk kind of moves. It's almost like one operator, and you move because of the symmetry of the problem. Because we considered this random distribution of sigmas in the disk, and so essentially, what you can do is you can replace this sum over partials by just K times a partial of with respect to a coordinate that is defined in the center of the disk. And so if you sort of carry the same logic through, you can compute, you can through these recursion relations, you can compute the pair creation. It gets modified by this factor of 1 upon K raised to the n plus 1. And so this is sort of a picture we tried to develop, Ben's intuition, that we thought we could maybe understand something about. This is just one quantity, but of course we'd like to go and see if we can do more things. And so this holds for large K, and then M and N is sufficiently large because if K is large, the low energy excitations really aren't going to be there because the twists are so close together, and so you're only getting short distance physics because of the separation of the constituents that was made by the twist operator. And so, but this is one quantity that we, at least with these arguments, we were able to compute. So I think I'm probably very short. I think I'm kind of short. So.
More than 10 minutes.
I have more. Okay. Oh.
More than.
Okay. So what we've done. So just to conclude. What we've done is we've derived the effect of the twist operator using what we call a weak variable ansatz, this and conformal symmetry. So we use the Virasoro algebra to give us these to reproduce the effects which are known for one twist. And so we've computed what's pair creation, propagation, and contraction. These are the three main processes that you'll get And we've shown that the results do agree with the methods from the covering map. And we were able to find, at least in a simple, very symmetric scenario, we were able to find just the coefficients of pair creation for a simple multi-twist scenario. So for future, what we like to do is extend the results for the multi-twist. And we like to, just as a matter of completion, we like to repeat this for fermion modes. Because then this would basically have both components that would help us to derive these effects in the D1D5 CFT, which is superconformal. And one of the major hopes here is, so in the D1D5 CFT, you have something called a marginal deformation. And this is what takes you from the free orbifold point to the supergravity point, but typically it's really hard to go far away. And we know that the supergravity point is pretty far away, I think, in modular space, but we can only compute things to say first or second order. The hope would be that we could use superconformal symmetry now to bootstrap the marginal deformation, which includes, so the marginal deformation is, it's given by a twist. So yes, let me make that clear. The twist operator is a part of the marginal deformation, but it also includes like a supersymmetric operator because it's a superconformal field theory. And so G here represents this supercharged operator. It's a marginal operator. And if we could bootstrap maybe any, I don't know, maybe any effects, it may help us to understand better the holography far away from the orbifold point. And so maybe we could have some type of non-perturbative description of certain quantities, which would really help us match the supergravity. Maybe, I mean, I understand this is very ambitious. I'm not saying that, I don't even know how long, or, you know, maybe there's some things that it would be hard to actually do this. But, you know, just thinking about understanding like the formation of microstates, dynamics, things like that, things which typically are non-perturbative effects. We like to try, if we can, to do that with this method, because again, the crucial step is that we don't have to use the covering map this time, and so that would be the hope. And also, I also guess I didn't mention also, maybe you can also start in the initial state. You can start with multi-wound sectors, and so what we considered in the initial state here was single wound sectors. But you can also start in the initial state with multi-wound sectors, and so then, but I think in that case it would be more. I think it would also be more difficult. But you can also start with a bunch of. You can also start with many single wound states, and then you could just twist up to a long winding state and see. There's many different like scenarios, but I guess certain processes may be more entropically favorable than others. So anyway, there's a lot of directions that you could hopefully go with this, and so thank you. That's all I have, and thank you.
Questions? Please.
So you use large K. Yeah, sorry.
At large K, you had one of the three things. What about the other properties? The other two properties?
So we didn't look at it yet, but yes, we haven't looked at it yet.
Okay, but are you optimistic you can do it?
I want to say yes. I'm going to be the optimist.
Right.
And I'm going to say that maybe in some regime we can. So I'm not, I don't know the details of what it would look like now, but the gammas seem to be sort of the easiest sort of equation that you get out of this. It's like the sort of the easiest consistency condition comes from the pair creation. But I mean, definitely want to look at hopefully we can. That'd be great if we could.
So just sort of trying to set this in perspective. I mean, when I think about dropping a single graviton into ADS, then what happens is that single graviton creates two left-moving states. It hits a twist operator, it fractionates, it keeps fractionating, and then by some miracle, it reassembles itself when it comes back out again as the graviton passes through the ADS, comes back to infinity. So does this Bogoliubov transformation sort of give you insight into how you see the exact holographic drill of a graviton dropping into an ADS and then coming back out again?
Actually, yeah, so this is so this Boglegrove transformation. This is what we actually use to compute the when we when we looked at this oscillation mode. When you drop it in this ADS3, and it goes in and comes out. It has this periodic behavior. This is what we used, but we used the covering space method, and so we did use that in that case. But that was a weak. That was at order 2 in the twist, and so it's hard to say. Yeah, it's hard to say because in the gravity theory, in supergravity, it's the coupling is large, and so. But at least at weak coupling, it shows this periodic behavior. But the hope would be like you said, there's many twists, not just 2. There's many of these that's happening as you drop it in. So if we actually look, we get a probably more accurate picture if we look at multi-twist. As it's you have the left and right mover. So you start with the left and right mover, and you act multi-times with a twist because in principle, I guess the twist is continuing to act. Yeah. It was really hard to compute before. It's still.
But there should be some universal statement because when you drop something into ADS, it starts off as a single part, two open strings going in the opposite direction, and then when it comes out, it's the same thing. And in between, it's turned into this completely scrambled mess. And so this Boglegrove transformation must get inverted as it swings through the bottom of the space.
Yes, no, I agree. It is. It's amazing how because it's supposed to. Because if you drop something in ADS, nothing's supposed to go in and come out. And so it is interesting. It's something is sort of things that are conspiring together, even if it's many terms. And me and Ben talked about this with Samir and about this, what's actually happening. It seems like that somehow things are conspiring, even though you have this complicated twisting going on. That somehow it cancels out or something happens and it comes out the other, it comes back together.
Well, that's why I was hoping your large N or large K limit would give you some insight into how the Boglegrove transformation gets inverted as the thing swings through a period.
Yeah. So what we would need to do is look at the F function because that's what you get when you start off with an initial mode, and so we would need to look at the multi-twist acting on the F function. I think it may be able to say something about that. So, yeah.
Other questions or comments by David? Wow, that was great.
Okay. Nice talk. Thank you, Shaun. Just a detail probably, but so you had this nice weak Boglegrove ansatz. Where you didn't assume in advance the condition that gamma was equal to alpha inverse beta or whatever it is. At the end of the day, did it turn out that alpha times gamma was equal to beta as?
Okay, we didn't check explicitly, but I think that's probably the case because the alpha and the gamma they all match the twist, the covering space map, the computations. So okay. I would be willing to say that they do match.
So then they will, yeah.
I would think, yes.
Yeah, right. Because things are delicate because you're dealing with infinite dimensional matrices, infinite size matrices. But that's an important consistency condition that you have that relation at the end of the day, just so that you're sure that each thing that is supposed to be a vacuum for its own sector is still a vacuum. So.
Right. And actually we can go back and
okay,
test
but if you checked it matches the covering space methods, then that does hold. So
I think so. Yeah,
thanks.
I think it does. Yes, no problem. Thanks.
Other questions or comments from Zoom?
I don't think so.
No. Okay. So let's thank again Shaun and there's a